We'll move on to the next part of your magnetic field chapter. Okay. All the examples we've done so far concerns magnetic force acting on wires. The next examples that you will talk about will be magnetic force on moving charges. Okay, so as I mentioned to you earlier before, moving charges produce their own magnetic field, so they act like their own magnets. If you place it inside another separate magnetic field, the moving charge will experience a magnetic force. Okay, so now say for example right now I tell you I have a magnetic field that is going into the plane of the paper or the plane of the screen right now, indicated by this series of X here. There's a magnetic field going into the plane of the paper, and then now I tell you you have a positive charge that is moving perpendicular into the magnetic field. All right, say right now this is the view right now from the top. You know the magnetic field is going into the plane of the paper. You have a charged particle that is moving perpendicular to the field. If I'm interested to know what is the magnetic force acting on the moving charge, the magnetic force is actually given by this equation. Okay, Fb equals to BQV. All right, this one is for moving charges 90 degrees to field. The one you learned before this is this one. Fb equals to BRL. This one is for wires at 90 degrees to field. Okay, they both talk about magnetic force, but they are applied for different things. One is for wires, another is for moving charges. So which one to use depends on what case are you considering. All right. Now for the case of a moving charge that is moving perpendicular to the field, what we will tell you is that for a charge that is moving perpendicular to the magnetic field, it will always be moving in a circular path. Okay, now because of this reason, you see when you're talking about something that's moving in a circle, this one is from the first chapter of your A2. When something is moving in circular motion, say this is the center of your circle and then this is the object, I can tell you that the object is here, 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 and here. And then after that, if I'm interested in the object at the different points, I will say that the linear speed is going to be in this direction, right? Okay. Now, how is it that an object can move in a circle was mainly due to the fact that that time we told you if your object is able to move in a circle with constant speed, that is mainly due to the fact that there's always a force causing it to move in a circle, and that force is actually always directed towards the center of the circle, isn't it? If you have something that moves in a circle with constant speed, meaning you say same magnitude all the time, if this one is 10 meter per second, this one would be 10 meter per second, this one is 10 meter per second, and then this one is also 10 meter per second. The only way it can move in a circle with constant speed, constant magnitude, is if your force is directed towards the center of the circle. That force is actually your centripetal force. Okay. Now here the key takeoff point was that to move in a circle with constant speed, there must be a force to continuously change the direction but not magnitude of the speed, but not magnitude of velocity. Okay, to move in a circle with constant speed, there must be a force to continuously change the direction, but not magnitude of the force, the magnitude of the velocity. Okay, so this force must therefore always be perpendicular to the velocity, to the direction velocity, or always directed towards the center of the circle, or always directed towards the center of the circle. Okay, so this force is the centripetal force. Okay, that must be provided by some other existing force. That must be provided by some other existing force. Okay, right. So to recap, when you're talking about circular motion, if you want something to move in a circle with constant speed, with unchanging magnitude or speed, there must be a force present to continuously change the direction, but not the magnitude. Okay, so to be able to change the direction but not the magnitude, it means that the force must be perpendicular to the direction of the velocity. Okay, that time I think I give you guys an example like this. If you have velocity this way, but you have force or acceleration this way, your magnitude is unchanged, but direction changes. And then likewise, I also give you this example. If your V is this side, but your F or A is this side, your magnitude changes, but not direction. Okay, and then likewise, if I give you an example like this, that time, when I told you your V is this side, but your F and your A is at the angle theta here, this one what will tell you is that magnitude and direction changes, because what will happen is that this force or acceleration here can be resolved to two perpendicular components. You can have a F and A in this direction, you can have F and A in this direction. The one in this direction causes you to change magnitude, but the one in this direction causes you to change, the ones that is this part here, the horizontal one which is parallel to the velocity here, this one causes you to change magnitude but not direction. But the ones that is vertical here, perpendicular to your velocity, will not cause change in magnitude but change in direction. Okay, so that's why here we say that magnitude and direction both changes. But if it's not an angle, it's either just parallel to the velocity or perpendicular to the velocity, then only one of these changes will happen. If it's in the same direction as my velocity here, I would say magnitude change, but not direction. But if it's perpendicular to my velocity, the magnitude won't change, but the direction will change. So like in the case for something that's trying to move in a circle, if it's moving with constant speed, but the direction is continuously changing because it's moving in a circle, the force must always be perpendicular to the direction of motion or direction of velocity. Okay, now it's because it's always perpendicular to the direction of velocity or motion that your force or acceleration will always be directed towards the center of the circle. Okay, both of these mean the same thing. They will imply the same thing. If something is moving in a circle and the force and acceleration is always perpendicular to the direction of velocity or motion, that force or acceleration will always be towards the center of the circle. Okay, they will imply the same thing. Okay, and that force is your centripetal force, or that acceleration is your centripetal acceleration, which usually must be provided for by some other existing force. Okay, so now how does this relate to your moving charge moving in a circle? It's because of your Fleming's left hand rule. Remember, your Fleming's left hand rule was this one here. Okay, where we tell you this one is FB, the thumb is your magnetic force, the index finger is your magnetic field, your I is your current. Now, if you look at your right, left hand oriented to according to left hand grip rule, you will notice that all of these components are actually perpendicular to each other. FB is perpendicular. FB are always perpendicular to each other. Any one of these will always be perpendicular to the other two. Okay, so now what we'll tell you is that when you have a moving charge that is moving in perpendicular to your magnetic field, your magnetic force will always be perpendicular to your direction of velocity or your direction of motion. Your direction of motion or direction of velocity is actually represented by this I here. Okay, this I is actually conventional current. Okay, it is actually flow of positive charge. Okay, this is important. You will see later. When you're talking about Fleming's left hand rule, the I is always the conventional current, the flow of positive charge. So it indicates to you the direction of motion or direction of velocity of the charge. So like here, you will see that no matter how when you are using Fleming's left hand rule, no matter how you change the direction of your current, no matter how you change it, the FB will always be perpendicular to your I. Okay, in other words, your direction of motion of your charge will always be perpendicular to your magnetic force. Okay, so your direction of motion of your charge or velocity is always perpendicular to your force. It will always be moving in a circle. Your magnetic force here is acting as your centripetal force to allow your charge to move in a circle. Okay, how is it possible that a charge can move in a circle? Is because from Fleming's left hand rule, you see that no matter how the direction of current change, no matter how the direction of your charge changes, FB is always going to be perpendicular to it. So this one already satisfies the requirement for it to move in a circle. Okay, so because your thing is moving, your charge is moving in a circle right now, you have centripetal force, and centripetal force must be provided by some other existing force. That force that is providing you that centripetal force is actually your magnetic force. Okay, so it's your magnetic force, right? So in your case here, if you're talking about magnetic force providing you your centripetal force, FB is equals to FC. Magnetic force acting on the charge moving perpendicular to the field will be BQV. Centripetal force will be mv squared over r. Alright, so it's from here then you can find a few things. If you want to manipulate the radius of turning of your charge inside a magnetic field, BQV equals to mv squared over r. R in turn will just be mv over BQ, right? If you want your radius to be smaller, all you just need to do is that you use smaller mass, you use smaller velocity, or larger magnetic flux density, or larger charge. Okay, so those are one of the things that you just need to know. Okay, right? So if there's anything that I need you to really be careful about, is something to do with Fleming's left hand rule. The FBI here that I always told you, just bear in mind, keep in mind that this I is always conventional current is always flow of positive charge. Okay, meaning to say it will always be opposite in direction to flow of negative charge. Okay, this one is conventional current. It's meant to indicate the flow of positive charge. Okay, it will always be opposite in direction to flow of negative charge. All right, if let's just say in your current case, next time you see a question where the charge is not positive, but the charge is negative, you need to know that if you want to find out the I must be opposite in direction to the motion of the negative charge. Okay, so that one just keep in mind first. All right. Okay, so I think it's better we just start with a question to do. All right. Yeah, before I go to that, there's just something like a summary or things that I need to tell you about. Okay, this one is under page 12 of your notes. Now, you've learned a bit about the forces acting in gravitational field, electric field, and magnetic field. Now, force on gravitational field, gravitational force only affects mass. Okay, whereas electric force only affects charges. It won't matter whether the charge is moving or stationary. As long as it has a charge, it will have electric force. But as for magnetic field, you only have a magnetic force if the charges were moving. So as I mentioned to you, only moving charges produce their own magnetic field, such that if you place it inside another magnetic field, they will experience a magnetic force, because then it's like you putting a magnet inside another magnetic field. Okay, so magnetic field, you have magnetic force only if the charge moves. If the charge doesn't move, the charge does not have a magnetic field. You putting it inside another separate magnetic field will not cause it to have a magnetic force. Okay, so this is one thing that you need to be careful about. And then when you're talking about the direction of force acting on the three different fields, what we'll just tell you is that gravitational force will always be in the same direction as the field, whereas electric force will either be in the same direction or opposite in direction to the field. If you're talking about gravitational force, I think I better just draw this out for you. You're talking about gravitational force. This is your gravitational field, right? Okay. If you place a test mass here, the direction of the gravitational force will always be in the same direction as your gravitational field. Okay. If you're talking about electric force, the direction of the electric force will either be in the same or opposite direction to the field. It depends on charge. It depends on the charge. What do I mean by that is, if you have something like this, a positive charge whose field lines is like this, all going out, and the negative charge whose field line is like this, all going in. If you place a positive test charge, this and this will repel. Your Fe is this side. If you place a positive test charge here, this and this will attract, so your electric force is here. So you see, in your current case here, your electric force will either be in the same direction or opposite direction to your field. It depends on the charge that you have. Okay, so that's okay. Now, for magnetic force acting on the charge or moving charge, the magnetic force will always be normal to the direction of the field and motion because of Fleming's left-hand rule. As mentioned to you just now, Fleming's left-hand rule was this one. This one is your FB. This one was your B. And this one was your I. I told you that any one of these will always be perpendicular to the remaining two. Okay, so no matter how you change the direction of any one of these, the other remaining two will always be perpendicular. Okay, so your magnetic force is always normal to the direction of your field and your motion. Okay, so that part is okay. Now, if you want to find out the magnitude of the gravitational force, electric force, and magnetic force, Fg is equals to mg. You do not have any expression for speed in it. You will say that gravitational force is independent of speed. Likewise, electric force is Fe equals to Eq. You notice that there's no expression for speed inside. It's also independent of speed. Okay, so gravitational force, electric force has nothing to do with speed. You can move faster, you can move slower. You're not going to change the magnitude of the force. But when you're talking about magnetic force acting on a charge is Fp equals to BQV. There's an expression for speed inside. So this means that if your speed increase, your magnetic force will increase. If your speed is 0, your magnetic force will just be 0. Okay, so there are cases where you need to be careful about magnetic force. You just need to know that if the charge is stationary, V is 0, magnetic force is 0. Another case could also be when the charge is moving parallel to the field, you will not have magnetic force. Okay, so these are two conditions in which you will never have magnetic force. If your charge is 0, so if your charge is stationary, not moving, or is moving but parallel to the field. Okay, so that time I mentioned to you, only charges or current perpendicular to magnetic, only moving charges and current perpendicular to magnetic field can produce magnetic force. Okay, this was one thing I think I mentioned in passing to you previously. Only moving charges or current perpendicular to magnetic field can produce magnetic force. If it's parallel to it, no magnetic field whatsoever. Sorry, if it's parallel to it, it's parallel to the field, no magnetic force whatsoever. Okay, so just bear in mind these two conditions. If the charge is not moving, no magnetic force. If the charge is moving but is parallel to the field, you do not have magnetic force. You must have perpendicular to the field. Only then can you have magnetic force. All right. Okay, so let's do an example. You can have a look at page 1. It relates to what I just mentioned to you. Okay, so I can look at that one. Okay, now this is June 15 P41. Question 6A. Which is this one. Okay, wait, where is it? Question 6A. Okay, now they're asking you state the type of field or fields that may cause a force to be exerted on a particle that is uncharged and moving. Okay, now what kind of fields may cause a force to be exerted on a particular particle that has these conditions, has these situations? Now, a particle here already implies to you it has mass. Okay, so gravitational field definitely would affect the particle. Okay, but if the particle has no charge and moving, you know that because it has no charge, electric field and magnetic field will not affect it. As I mentioned to you just now, electric field would affect charge. Magnetic field would affect moving charge. In other words, both must, for electric field and magnetic field, minimum you must have charge in the first place. But here they're saying to you your particle has no charge and is moving. The fact that it doesn't have any charge means that electric field will not affect it, magnetic field will not affect it. So the only field that can cause a force to be exerted is just gravitational field because the particle has mass. All right. Then what about a case where the particle is charged and stationary? So as mentioned, the particle has mass, so gravitational field can exert a force on it. It has charge, so electric field can exert a force on it. It is charged but stationary, so magnetic field cannot exert a force on it, because for magnetic field you need to have both charge and the fact that the charge is moving. So here it is charged and stationary, it is not moving, magnetic field will not affect it. So only gravitational and electric. Okay, so that part is fine. Then after that, if you look at the last one, they tell you that the particle is charged and moving at right angles to the field. So same thing, particle has mass, gravitational field will affect it. It is having a charge, doesn't matter whether it's moving or not moving, as long as it has charge, electric field will definitely affect it. Now it is charged and moving at right angles to the field. Okay, so it's moving and is at right angle to the field. So definitely magnetic field can affect it. So when you say magnetic field moving at right angles to the, when you say a charged particle is moving at right angles to the field, it could mean something like this. Say this is your magnetic field in this direction. Your charged particle is moving like this with a velocity v. So this charged particle moving at right angles to the magnetic field here will experience a magnetic force. And the direction of the magnetic force will be determined by Fleming's left-hand rule, according to this. Okay, right. So this one is okay. Now, particle X has mass 3.32 times 10 power minus 26 kg and a charge of 1.6 times 10 power minus 19 coulomb. The particle is traveling in a vacuum with a speed of 7.6 times 10 power 4 meter per second. It enters a region of uniform magnetic field that is normal to the direction of travel of the particle. The particle travels in a semicircle of diameter 12.2 centimeter. For the uniform magnetic field, state is direction. So as mentioned to you, the moment you see that they tell you the charged particle is entering the magnetic field perpendicular to it, it will always move in a circle because the magnetic force always acts perpendicular to the direction of motion of the particle or direction of velocity of the particle. So it will always move in a circle. So the charged particle enters and then it moves in a circle and then it goes back out. Now the question is just asking you, for that uniform magnetic field, state the direction of the for the magnetic field state its direction. How are you going to know whether it's into the plane of the paper or out of the plane of the paper? Okay, so the way to do that will be just by looking at this point here. You can put any point up, but the easier point to consider is here. Okay, now you consider this point here. They tell you that this one is a charged particle and it is positive. Okay, so say consider your charged particle here, positive. At the point where it just enters the field, and the point where it's at this circle here, this part of the circle here, your velocity will be here. Okay, this is the flow of positive charge in this direction. So this is also the direction of your conventional current, because I mentioned to you I conventional current is the flow of positive charge. Okay, maybe I reword this. Conventional current I follows the direction of flow. It follows the direction of flow of positive charge. Okay, if you see a positive charge moving this way, this is the direction of your conventional current. Okay, then after that, because you're moving in a circle like this, specifically at this point, you know that the centripetal force is causing your charged particle to move in a circle, and the centripetal force is actually your magnetic force. So at this point itself, you ought to be able to guess that the magnetic force must be going in this direction towards the center of the circle. Okay, because only then can you turn and make a circle, right? So you've already identified the direction of your I, you've already identified the direction of your B. So you can use Fleming's left hand rule already. You orientate your fingers according to the Fleming's left hand rule, where I is going outwards and then FB is going towards the right. You will notice that your index finger, which represents your magnetic field, is actually pointing towards you. It's actually indicating to you that your magnetic field is acting out of the plane of the paper. Okay, so for this case, identify first what is your I, identify what is your B, sorry, your magnetic force FB, then you can identify what is your B already. Right, so this part is fine. Okay, the term to use will always be out of plane of paper or into plane of paper. Don't write something like upwards. I mean, when you're looking at a piece of paper, it seems to be that the magnetic field is acting outwards, but that isn't a correct term to use. You need to say out of plane of paper or into plane of paper. Okay, right, so this one is okay. Now calculate the magnetic flux density here for the thing that's moving in a circle. So here you can just say that magnetic force provides you the centripetal force. Fb is equals to Fc. The magnetic force acting on a moving charge 90 degrees to the field is BQV. Centripetal force is mv squared over r. So from here you can find out what is your B. Your mass is given, your velocity is given, the charge is also given, then your r is the radius. What you are given here is the diameter. You need to divide by 2 to get the radius. So eventually you get your answer as 0.259 Tesla. Okay, so you get the answer as 0.259 Tesla here. Okay, right, so that part is fine. Then part C, they tell you you have a second particle Y with a mass that is less than particle X but having the same charge. It enters the region of uniform magnetic field in B with the same speed along the same initial path as particle X. Same charge, same speed, same path, same initial path. So they're asking you right now, on the figure, draw the path of particle Y in the region of the magnetic field. Okay, what should be the path of the particle now? Now, if you have a charged particle entering perpendicular to the magnetic field, you're still going to move in a circle. But the question now is, if it's moving in a circle, how big or small will the radius be? So just now you know that FB equals to FC for something, a charged particle that moves in a circle, eventually you got this expression, right? B is mv over qr, bq, because it came from bqv over equals to mv squared over r. So now there are a few things that you could see. The question says that you're entering the same field as before, so B is constant. You're entering with the same speed, so V is constant. And you're also entering with the same charge, so Q is constant. So what you can do now is that you will eventually come to the conclusion that if all these three are constant, that means mass is directly proportional to R. Okay? So if your mass is now lesser, that means your radius will be lesser, because the question already told you the mass is less, right? Yeah, they told you the less mass. So since your mass is less, your charged particle will be moving in a circle but with a smaller radius. So you just draw a circle, just make sure that the radius or diameter is smaller than the original one, and you will be fine. Okay, so that part is fine. Then after that, you can have a look at page 9 if you're okay with that. The last question I can probably go through with you is page 9. Okay, so have a look at page 9. Not this one. Page 9, this one. Okay. November 16, P41. That one would be question 7. Okay, so the first few questions is actually kind of like the same as before. So you just say this now. Yeah, that's part B. Part A, explain what is meant by a field of force. A field of force is just simply a region of space where a force is experienced by a particle. They're not asking you to define gravitational field, electric field, or magnetic field. They're just asking you to define what is a field of force in general. It's just simply a region of space where a force is experienced by a particle. Okay, you don't need to describe anything more because they're not relating specifically to gravitational, electric, or magnetic. So you don't need to say anything more. Okay. Now, state the type of fields or fields that may give rise to a force acting on a moving uncharged particle, stationary charged particle, a charged particle moving at angle to the field or fields. So here what we would just say is that if you have a moving uncharged particle, as I mentioned to you, has mass. Therefore, gravitational field would affect it. But it has no charge. So electric and magnetic is out. So only gravitational force, only gravitational field here. So if you look at the second part, stationary charged particle has mass, so gravity will affect it. It has charge, so electric will affect it. But it is stationary, not moving. The charge is stationary, not moving. So magnetic is out. Okay. Then likewise, if you look at the last one, a charged particle moving at an angle to the field of fields. Particle has mass, gravity will affect it. It has charge, electric will affect it. So you have a charged particle moving at an angle to the field of fields. That one is akin to you saying something like this. Your field is like this, but your charged particle is moving at a certain angle theta. Okay. So since it's moving at a certain angle theta here like this, you can actually resolve the motion into two perpendicular components. You would have a perpendicular component of velocity here. You have a parallel component of velocity here. So this one here will cause magnetic force. This one here does not cause magnetic force. As I mentioned to you, only charges or current perpendicular to the magnetic field will produce magnetic force. So this part here won't cause magnetic force, but this one here will. So if your charged particle moving at an angle, there is a component perpendicular to the field. So magnetic field won't actually affect it. Alright, so that part is okay, right? Okay, now then you go to the second part. This part I'll just explain here. Alright, so let me clear off the drawings. Wait, I don't need to clear that. They tell you an electron mass m charged negative Q is moving at speed v in a vacuum. It enters a region of uniform magnetic field of flux density B as shown. Initially, the electron is moving at right angles to the direction of the magnetic field. Explain why the electron moves in the arc of a circle. Okay, they're asking you to explain why does the electron move in the arc of a circle. Now, this part is related to just now what I mentioned to you regarding Fleming's left-hand rule, which is basically this one. I mentioned to you that when your current here actually represents the direction of motion or direction of velocity of your charge. So no matter how you change the direction of your velocity, the direction of your current, your magnetic force will always be perpendicular to it. Okay. So because your magnetic force is always perpendicular to your direction of velocity from Fleming's left-hand rule, which you can see here, it means that your charged particle will move in a circle. All right, your magnetic force is providing you your centripetal force right now. Okay, that part is clear. Now, here there's one thing here you will also need to talk about, because this one is 3 marks. The part where I say magnetic force is always acting perpendicular to the direction of motion of the particle. That part you understand how it causes you to have circular motion. The other part, the magnetic force provides you the centripetal force causing the electron to move in the arc of a circle. This one you also understand. These 2 points are related, directly related to each other. This one gives you your 2 marks. But where did the 3rd mark come from? The 3rd mark comes from this. The magnitude remains constant. Okay, now Fc is equals to mv squared over r. Now your Fc is provided by Fb. Okay, now you can see from here that Fc is actually inversely proportional to R if everything else remains the same. Okay, so if Fc or your Fb is constant, R is constant, therefore motion is a circle, right? Now your magnetic force here will always be constant, because here you see you're moving in the arc of a circle, you're moving with constant speed, your magnitude did not change. So your mass did not change, your velocity did not change, your centripetal force by right would, sorry, this one is Fb equals to BQB, right? If your magnetic force is always perpendicular to your direction of velocity, you will never change your magnitude. So V is always the same, charge is always the same, magnetic flux density is always the same, your force is always the same, your centripetal force will always be same. Okay, your centripetal force has a direct relation to your circle that you do, that you move. If your Fc is the same, your R is the same, so you will be moving in a circle. Now if you're moving in a circle, it's like this. You will notice that your radius is constant for a circle. If your Fc is not constant, your radius is not constant, you won't be moving in a circle. Instead, you will be moving like this, you see. You'll be moving in the arc, you'll be moving in a spiral like this. So when you try to see the radius, you see this radius is different from this radius is different from this radius. So if r changes, it becomes a spiral. Okay, so here they want you to explain why does it move in the arc of a circle, specifically why it moves in a circle. Another thing you needed to explain is the part where the magnetic force is constant. Because the magnetic force is constant, your centripetal force is constant. That ensures that your radius itself is constant. So this one contributes to you moving in a circle. Okay, this is another factor. Okay, so that part is okay, right? So this is one part of it. Okay, then the other thing I'll just mention here is for part 2, they say derive an expression. If you guys haven't copied this, no worries. This one you can copy from Google Drive later. Okay, now for part 2, this one they just say derive an expression in terms of radius out of the path for the linear momentum of the electron, show your working. So for a charged particle that is moving in a circle, magnetic force provides centripetal force, Fb equals to Fc, so BQV equals to mv squared over r. Eventually, you can express this as mv equals to bqr only. Okay, so momentum is mv, so momentum is bqr. That's all there is to it. All right. Right. State what is meant by magnetic field, March 17, P42. Magnetic field is just a region where a force is experienced by a magnet, moving charge, or current carrying conductor. So any one of these would do. As long as you have the wording, a region where force is experienced, this is one mark. And then after that, you subsequently mention either is by a magnet, moving charge, or current carrying conductor. That one will be okay. Okay, you don't need to write all three, just need to write one. Okay, personally, I would not write just magnet itself lah. It seems too obvious. All right. Okay, so that part is fine. Right. So that one is fine. Then if you this one is from the notes. Okay, so if you need to copy, you can copy from the notes. Now for part B, you have a particle of charge positive Q and mass M traveling in a vacuum with speed V. The particle enters at right angles to a uniform magnetic field flux density B. So the question then subsequently asks you, the particle leaves the field after following a semicircular path of diameter d. State the direction of the magnetic field. So this one here, I mentioned to you, it is always best to just pick a particular point for your analysis. The easiest point to pick would be from at this point here. Okay, at this point here. All right. So at the point where your charged particle just enters the field, this one is a positive charge. Okay, and then because you're moving in a semicircle like this, you know that your magnetic force that is acting as your centripetal force must be moving in this direction towards the center, must be pointing in this direction towards the center of the circle. Okay, now when you look at the direction of the velocity of the charged particle at this point, it is actually moving here. Okay, and if you want to use Fleming's left hand rule, which I mentioned to you before, this one is magnetic force, this one is B, and then this one is I, right? Okay, so this one is B, and then this one is I. Okay, so the I mentioned to you is actually conventional current. In other words, it is flow of positive charge. So since you have positive charge moving in this direction, this is also the direction of your conventional current. So you use your Fleming's left hand rule now, where you try to orientate your fingers accordingly for the B and the I, which is this one and this one. You will see that your magnetic field is actually pointing towards you. Okay, your index finger will actually be pointing towards you. So your answer will be out of the plane of the paper or out of the plane of the page. Okay, so this one is fine. And then here the question is asking you subsequently, why does the speed of the particle, why isn't the speed of the particle affected by the magnetic field? Okay, right. So here you need to be careful a bit about the wordings that they use. The wording they use here is speed, not velocity. Okay. Now, if you're talking about velocity, velocity being a vector, you need to consider both magnitude and direction. But speed is different from velocity. It's just scalar. Okay, you only need to consider the magnitude. All right. So the question here is asking you, why is it that your speed of your particle itself is not affected by the magnetic field? They're not asking to you. They're not asking you about the velocity. If they're asking you about the velocity is actually affected by the magnetic field, because if you try to think of it a little, if I consider a few points on the magnetic, a few points as the particle moves in a circle, the direction of my velocity will be like this, like this, like this, like this, and like this. So it could be that they have the same magnitude. This one is all 10 meter per second, 10 meter per second, and then 10 meter per second. The magnitude here is the same, but the direction has changed. So in your case here, you have considered the velocity to have changed. Okay. But here, if you just consider speed, speed is talking about the scalar part. Okay. It's just talking about the magnitude part. So speed is scalar. You only need to consider magnitude. You don't bother about direction. Here they ask you, why is the speed constant, not affected? So you are trying to explain why does the magnitude always remain constant. All right. So it has something to do with what I mentioned to you guys before, where I told you if you have velocity this side, maybe I just draw a few cases. Okay. If you have velocities like this, but your direction or acceleration is slightly different, where I tell you that here maybe your acceleration is like this, here maybe your acceleration is like this, here maybe your acceleration is like this, and then here maybe your acceleration is like this at a certain angle. Okay, at a certain angle theta, say for example. Okay, so what you could say here is for these two, the direction does not change. Okay, magnitude changes. Okay, but so this one, if this one the acceleration is perpendicular to your direction of motion of velocity, this one magnitude unchanged, but direction changes. And then you're talking about the last case here, where you have the acceleration at a certain angle. You have ay this side, and then you have ax this side. The perpendicular component will cause your direction to change. The parallel component which cause your magnitude to change. Okay, so this one you will say that it is both magnitude and direction change. Okay, in general, if your acceleration is parallel to your direction of motion, in other words, there's a component parallel to your motion or velocity, your magnitude will change. Okay, and if you have a acceleration or component of acceleration that is perpendicular to your direction of motion velocity, it will cause your direction to change, but it will not cause your magnitude to change. Okay, so say like for the last case here, for this one at a certain angle, you actually have a component parallel and a component perpendicular. That's why you have both magnitude and direction change. Okay, now for the case of your magnetic field that causes a magnetic force acting on the charged particle, you remember the magnetic force is always perpendicular to the direction of your velocity because of Fleming's left-hand rule. If you use your Fleming's left-hand rule, you will notice that your FB, your FB and I will always be perpendicular. No matter how you change the direction, the FB and I will be perpendicular. The I is actually the direction of your current flow, or in other words, the direction of your charge motion. Okay, so it will always be perpendicular. So here, your magnetic force on particle is always perpendicular to the velocity. The magnetic force is the one that causes acceleration. So here, your acceleration your acceleration will always be in the direction of your magnetic force. Okay, so since your magnetic force is perpendicular to the velocity, your acceleration is also perpendicular to the velocity. There will be no changes in the magnitude, just the direction. Okay, your acceleration will be perpendicular to your velocity. There will be no changes to the magnitude, only changes to the direction. Hence, your speed remains constant because the magnitude did not change. But here it's worded as just this now. Because the magnetic force is perpendicular to velocity, there's no acceleration in the direction of the velocity, hence the speed remains constant. Okay? The force causes acceleration, and the acceleration is always in the direction of your magnetic force. Since magnetic force is perpendicular to your velocity now, the acceleration is also perpendicular to your velocity. There isn't a component of the acceleration in the direction of the velocity, so your speed remains constant. What it will cause is just a change in direction. Okay, right, so that part is fine. Okay, then another one you can talk about is part 3. They told you that show the diameter d of the semicircular path is given by the expression. If you're talking about the charged particle moving in a magnetic field moving in a circle right now, you know that the magnetic force provides centripetal force. Fp is equals to Fc. So magnetic force acting on a charged particle is BQV. Centripetal force is mv squared over r. You don't use mr omega square here because you have a term for v. All right. So BQV over equals to mv squared over r. The r you replace with d over 2. Radius is always half the diameter. So if you go and solve it accordingly, you will get 2 mv over bq. Right? So that part should be fine. So no issues with that. Okay. Then if you go to the second part of your question, all right. Now use the expression in B3, which is this one, to show that the time Tf spent in the field by the particle is independent of speed v. Okay. Now when your charged particle was moving, it was moving in this manner. Okay, in a semicircle. Alright. So you can just think of it as this. They want you to use your expression in B3, which is basically the part where you're talking about T is equals to 2mv bq. Okay, right? So what you can do to relate the distance moved with your speed v, here this one was talking something about the diameter. Sorry, the expression in B3 was talking something about distance moved or the diameter d. Okay, sorry, the expression in B3 was talking about the diameter. Then they want you to relate to the fact that the time spent in the field is independent of speed v. Okay, so you can just think of it as just this first. The speed v here is something you want to start with. You can just say that speed is distance over time. Okay, so the speed here could just be your v, all right, the velocity with which your particle is moving. Because you see, as I mentioned to you, your charged particle, no matter at which point it is moving right now, the speed is always v. The magnitude did not change. Okay, so right now I want to find out an expression that is based on this. So the speed is v. The distance moved by my charged particle inside the field is this one. It is actually the arc of it's actually half the circumference of a circle. Okay, this one, the distance moved is actually half the circumference of the circle. So half the circumference of a circle would be pi d over 2. Okay, because you know that the circumference of a circle itself is actually pi r, or 2 pi d. Sorry, not pi r. My mistake, sorry. The circumference of a circle itself is actually pi d, or pi 2 pi r. Sorry, I got it wrong. Its eigen is 2 pi r, or pi d. Okay, if you're talking about half of it, half of the circumference of a circle, it means that you need to divide by 2. So it becomes pi d over 2. Okay, I want to relate it to d because the expression in B3 was in terms of d. Okay, the expression in B3 was d, diameter. So if I want to relate the distance right now, which is actually half the circumference of the circle, I will actually relate it to d, the diameter. So it will be pi d over 2. Okay, and then the time spent inside the magnetic field, the question already told you it is Tf. Okay, so it will be pi d over 2 divided by Tf. Okay, and then this one is what you get. You get pi d 2Tf. Okay, get the expression pi d over 2Tf. Okay, now your expression in B3 already told you that d is 2mv over bq. So what you can do is that you can actually substitute it inside here, where you say it's pi 2mv bq 2tf v, until eventually you get the answer tf is actually pi m over bq. So your time taken inside the magnetic field actually has no expression for the v. So therefore we can say that tf is independent of speed. Okay, so that part is okay. The working that I showed here is more like I use v, I substitute inside. That's why I got this. Okay, I still got the same expression tf equals to pi m over pq. Okay, if you don't want to sub v inside here, instead you want to sub d inside here, you will still get the same answer. All right, that part is okay. Then after that, the next one you can have a look at is page 14. Okay, so have a look at page 14 if you're okay with this. So page 14 is the next one. Okay, right, so page 14 is actually the page after your current question. June 17 P41. So June 17 P41 question 7. Okay. Right, so an electron having a charge minus q and mass m is accelerated from rest in a vacuum through a potential difference of V. The electron then enters a region of uniform magnetic field of magnetic flux density B, as shown in figure 7.1. The direction of the uniform magnetic field is into the plane of the paper. The velocity of the electron as it enters the magnetic field is normal to the magnetic field. The radius of the circular path of the electron in the magnetic field is r. Explain why the path of the electron in the magnetic field is in the arc of a circle. So this is a 3-mark question. Okay, you will notice that for magnetic field, there's always that question that asks you to explain why does your charge particle move in a circle inside a magnetic field. There's usually just 3 points. Okay, the first point is you always saying that the magnetic force is always acting perpendicular to the direction of velocity. The second point, the first point is this. The second point is you saying that the magnetic force remains constant inside the field. And then the third one is you saying that magnetic force provides the centripetal force, thereby causing your electron to move in the arc of a circle. Because you know that for a case of something that moves in a circle, to be able to move in a circle, your centripetal force must always be directed towards the center of the circle. But at the same time, when it's directed towards the center of the circle, it is always perpendicular to your velocity. So you saying that the magnetic force is always acting perpendicular to the direction of the motion already implies to you is always acting towards the center of the circle. So it's your centripetal force. Okay. And the part where you say the magnitude of the magnetic force remains constant inside the field is related to this. The centripetal force is mv squared over r. When you're trying to move in a circle, your radius r is constant. Okay, so your radius r is dependent on your centripetal force. Okay, if your r is constant, if your fc is constant, that means your r will be constant. So you move in a circle. If on the other hand, your fc changes, your r will change. So you will no longer be moving in a circle. It could be that you're moving in a spiral now, where your radius keeps changing each time. Okay. Now your centripetal force here is your magnetic force. Okay. So your magnetic force was constant. That means your centripetal force was constant. That means your radius will be constant. So you'll be moving in a circle. All right. So there's one part there. Okay. Okay, so this part is fine. Then no issues here. Then I'll just fill off the diagram. Okay, now show that the magnitude P of the momentum of the electron as it enters the magnetic field is given by this. Show that the magnitude of the momentum of the electron as it enters the magnetic field is given by this. Okay, this one you cannot say FB is equals to FC like the ones you have previously done because of the wordings of the question. They tell you show that the momentum as it enters the magnetic field. That means you are not yet inside the magnetic field. Okay, as it enters the magnetic field, you are not yet in the field. Okay, so the part where you say FB equals to FC was for when you are moving inside the field. Alright, because when you are moving inside the field, only then you have magnetic force. From what the question described to you here, the momentum of the electron as it enters the magnetic field, it is not yet in the field. So you don't have magnetic force yet. Okay, so what they're actually describing to you is a case where your magnetic field was here. This is your B field. what is actually happening is that you have an electron that was being accelerated through a potential difference of V. Your case here was that they already mentioned that your electron is accelerated from rest in a vacuum through a PD of V. Okay, so what they are asking you now is to find out the momentum of that electron as it enters the magnetic field. Okay, so you are actually considering this part of the motion now. You're not considering this part because you're not yet inside. So you cannot use FB equals to FC. So for this part of your motion where you are actually accelerating the electron from rest to a certain velocity before entering the field, you can make use of what you have learned in your electric field chapter. Work done in an electric field is equals to the change in kinetic energy of the electron. So work done in an electric field, you know it is actually QV, Q times your potential difference. Then your change in KE is actually still supposed to be half mv squared minus 0 because you were starting from rest here. You reach a certain velocity v here. So your change in K is actually just half mv squared minus 0. Okay. So be careful about the symbol of the V you use. This is potential difference. This is velocity. They are not the same. They seem like they're similar symbols, but they're actually referring to different things. Okay, so don't accidentally cancel them off. So you get 2qv equals to mv squared. Then after that, what you want to do is you want to express it in terms of momentum, right? So you try to break this out into momentum. You get mv times v. And since momentum is mv, v is p over m, you sub this one into your equation, you sub this one into your equation, this is what you get. So eventually you get your momentum as square root of 2 mqv. Okay, so also go with that. Okay, so that one is okay. So okay, so I'll move on to the next one. Okay, now the next part of the question, they told you that the potential difference V is 120 volts, the radius out of the circular arc is 7.4 centimeter. Okay, so determine the magnitude B of the magnetic flux density. So they want you to determine the magnetic flux density B, and they give you the radius out of the circular arc. Here you can actually think of it as your charged particle is already moving inside the magnetic field. Okay, your charged particle is actually already moving inside your magnetic field. So you can use FB equals to FC. Then you get BQB equals to MV squared over R. Then eventually you get MV over QR. Alright. Now you need to realize that there's a way to change this in such a way that it relates to your previous question. Your paper 4, a lot of times, your subsequent questions always tends to relate to the previous one when it comes to calculation. So if they ask you to do this one here, there's a reason why they want you to do that. Because the subsequent questions is expecting you to use this. So since this one is asking you to find momentum, from FB equals to FC, you try to see how does it relate to momentum. You can see that after you try to simplify this one, the V is gone. This part is just left with MV, which is actually just momentum itself. So momentum is just this one. So you just sub in that equation, put in the values, you will get your answer as 5 times 10 power minus 4. Okay. Since this is an electron, your mass of electron is 9.11 times 10 power minus 31. Get from your data sheet. Charge of electron is 1.6 times 10 power minus 19. This one, if you can't remember, you can also get from the data sheet. Okay, so this part is fine. Okay, so this one no issues. All right, then if you're okay, then I'll move to the next one. Okay, now the potential difference B in C is now increased. The magnetic flux density B remains unchanged. By reference to the momentum of the electron, explain the effect of this increase on the radius r of the path of the electron in the magnetic field. Okay, this one here. By reference to the momentum of the electron, explain the effect of this increase on the radius r of the path of the electron in the magnetic field. If you increase the potential difference when accelerating the electron, would it have any effect on the electron as it moves inside the magnetic field? They ask you to refer to the momentum of the electron. Okay. Now, by looking at this one here, you can actually see very clearly that if B is constant, B and Q constant, P is actually directly proportional to R. If your P drops, your R will drop. Okay. Now your P is actually square root 2 MQV. Okay. Your V is actually proportional to P. So if your P increases, your potential difference increase, your P would increase. So subsequently, from looking at this equation here, if your P increases, your R would also increase. Okay, so because they say with reference to the momentum of the electron, you have to first refer to what happens to the momentum. Okay, you have to first refer to what happens to the momentum. You must make reference to it because the question says by reference to the momentum of the electron. You need to explain first what happens to the momentum of the electron. From the equation, P is equal to square root 2 mqv. If V is increased, momentum increase. And then from this part of the equation, where P is equal to BQR, if momentum increases, R would increase. Right? So this part is fine. Okay, then the next part would be 29, I think, page 29. There's another page, page 29. Okay, so let me get that sorted out. Okay, this one I think you can just breeze through it. I'll go to page 29, November 18, P41. Page 29, November 18, P41. So yeah, this one here. Now explain what is meant by magnetic field. We just done a similar question on that. So I don't think I'll go through this again. This is just a region of space where magnetic field, where magnetic force is experienced by a magnet, current carrying conductor, or a moving charge. Okay, that is just what it was. Now for part B, they tell you you have a particle of mass m charged positive q and speed v. The particles enters a uniform magnetic field of flux density b such that on entry is moving normal to the magnetic field. Okay, then they ask you the direction of the magnetic field is perpendicular to and into the plane of the paper. On figure 8.1, draw the path of the particle through and beyond the magnetic field. Okay, they don't just want the path of the particle inside the magnetic field, but they also want the path of the particle beyond the magnetic field. So what you can do here is basically this. you know that your charged particle, when it enters perpendicular to your magnetic field, it will move in a circle, in the arc of a circle, but you don't know whether it's going to be in this direction or in this direction. So how do you know which of those two directions will your charged particle move? You can again use Fleming's left hand rule, which is this one. This one will be your FB, this one will be your B, this one will be your I. So here you have charged particle coming in. At this point here, your velocity is straight, like this. Okay, this is the direction of your velocity. Okay, and then after that, they told you your B field is into plane of the paper, I believe. Yeah, they told you the magnetic field is perpendicular to and into the plane of the paper. So your B is into plane of paper. Okay, and then this one is your positive charge moving this way. This one is your direction of your conventional current. So you use Fleming's left hand rule, where you try to orientate your two fingers according to the B and I. You will notice that your magnetic force is actually going to be pointing upwards at this point. So since it's pointing upwards at this point, it's actually pointing towards the center of the circle. So you know your charged particle will move in a circular path like this. Okay. So at this portion here, you have FB equals to FC. You will move in a circular path. But what happens after you leave the field? Okay. Now, once you leave the field, at this point here, you have no more magnetic force. So your charge particle continues moving straight according to Newton's first law. Okay, this one will be according to Newton's first law. Without any resultant force acting on a particle or object, your object will just continue moving with constant velocity in a straight line. Okay, right? So that's how you got this shape of your graph. Okay, so this one is okay. All right, now then the second part here, they ask you, there is a force acting on the particle causing it to accelerate. Explain why the speed of the particle on the leaving the field is v. Okay, so there is a force acting on the particle causing it to accelerate. This one is actually referring to your centripetal force. I mean, they did not tell you specifically what it was, but from here you should be able to know that the force acting on the particle here is actually your magnetic force. And then causing it to accelerate here is actually causing your centripetal acceleration. Okay, this one causes particle to move in a circle. Alright, so the next part of the question, the next part of the statement told you that explain why the speed of the particle on leaving the magnetic field itself is v. Just now, when you look at this one, your charged particle enters with speed v. Why is it that when it leaves the field, it's also speed v? Okay, that's what the question wants to know. So if you know what, if you remember what you know, learn from circular motion, if you're talking about a charged particle at any point as it moves in a circle, your centripetal force is always directed towards the center of the circle. It is always perpendicular to your direction of motion or your direction of velocity. So as I mentioned to you just now, if you have a force or acceleration that is perpendicular to your direction of motion or velocity, it only has the effect of changing the direction. It has no effect in changing the magnitude. Okay, so here you can just say that the force is always normal to the velocity and direction of motion or direction of speed, so the speed will always remain the same. Okay, you have actually answered a similar question to this just now before, where they ask you why is the speed unchanged. You say that the force is always normal to the velocity. There's no component of acceleration in the direction of velocity, so your in the direction of the motion, so your speed remains constant. Okay, that one was, I think, this one, March 17 P42, the part where they ask you explain why the speed of the particle is not affected by the magnetic field. Magnetic force always perpendicular to velocity, no acceleration in the direction of velocity, hence speed remains constant. This one was worth 2 marks. If you have put the same answer here, you would still get the full mark. Here was actually just 1 point. It's the same question, just that it has a reduced number of points there. Okay, so magnitude of speed is unchanged. Okay, the speed is unchanged. Right, but if they ask you whether velocity is changing or not, velocity is changing because the direction is changing. Okay, right, so this part is okay. Then you move to part C. Now part C, they tell you the particle in B loses an electron, so its charge becomes 2Q. Its change in mass is negligible. Determine in terms of V the initial speed of the particle such that its path through the magnetic field is unchanged. Explain your working. Okay, so now they tell you your particle in B loses an electron so that the charge becomes positive Q, positive 2Q. Before this, it was positive Q itself. Now it changed to positive 2Q. Then the change in mass they told you is negligible. Find out in terms of V the initial speed of that particle such that its path through the magnetic field is unchanged. So you have another second charge particle that is moving inside your field, magnetic field, inside your B field here. Okay, they want to find out what is the speed of that particle in terms of V such that when it moves in a circle inside the magnetic field is the same as the original particle. Okay, the path through the magnetic field is unchanged, is implying to you that your R must be same. Okay, so there are a few things you can just deduce from there. When you're inside the magnetic field, your charged particle moves in a circle. Magnetic force provides centripetal force. Fp is equals to Fc. You get BQV mv squared over R. Then V is BQR over M. From what you can see here, there are a few things that are the same, constant between the two cases. You are moving through the same magnetic field, so B is the same. They told you the change in mass is negligible, so mass is the same. And then they specifically say to you the path in the magnetic field is unchanged, so R is unchanged. So if all of these are constant, B constant, M constant, R constant, that means V is proportional to Q. So V2, V1, Q2, Q1. V2 is your V prime, V1 is the original V, Q2 is 2Q, Q1 is the original Q. So eventually you get your V prime as 2V. Okay, so this part is fine. This one you have to use ratio. Okay, so that one is page 29. Okay, so that part is fine. Last week I sent to you guys some separate past years that is actually from the more recent years. I think in your chat group I sent to you pages 35 and no wait. Yeah, I sent to you page 36 and 37 separately, right? There were two different sheets that I sent to you last week. The first one was November 19 P41 for parallel wires. And then after that, I sent to you another separate sheet, which is from page 36 to 37. Okay, which is actually talking about June 19 P42. So Roxanne Naoki, you don't have this inside your original past year question booklet. That's why I sent it to you guys. Alright, so this one is what I want to discuss next before I go through your velocity selector, another part of your chapter. Okay, for this part here, if I go back to the magnetic field chapter, wait, where's my magnetic field? Okay, right. As I mentioned to you before, if you have a charged particle that is moving perpendicular to your magnetic field, you will always be moving in the arc of a circle. You will always be moving in a circle. Alright, where you can say FP equals to FC, BQB equals to MV squared over R. Now, there are some cases where your charged particle, when it enters the magnetic field, is not exactly perpendicular to the magnetic field. It could be that it is moving at an angle to the magnetic field. So if it is moving at an angle to the magnetic field, you need to consider the motion in two different directions. Okay? The motion in two different directions will cause your charged particle to move in a helical pattern, a helix. Okay? Like in your case here, if I talk to you about just charged particle moving perpendicular to the field, it will move in the arc of a circle. It will move in a circle. But if it's moving at the angle theta to the field, it will move in a helical pattern, like a spring, like this one here that you see here. So how does it even produce a helical pattern here? How does it even move like that? It's after you consider the motion in two different directions. Okay, so say for example, right now you have a magnetic field B that is pointing towards the right here. Okay, and then you have a charged particle that is moving at the angle theta to the field. It enters the field at the angle theta. Alright. So what will tell you then is that you need to consider the motion in two different directions. So your velocity, you have two different components. One is the perpendicular velocity and one is the parallel velocity. Now the one that is the component of velocity of the charged particle that is perpendicular to the field, this one is what produces magnetic force. This one, the component of velocity parallel to the field, this one has no magnetic force. Okay, right? So the component of velocity of the charged particle perpendicular to the field causes you to have a magnetic force. But when you want to calculate the magnetic force, you do not straight away use FP equals to BQB straight like the ones before. This one is only when your charged particle is already perpendicular to the field. If it's not perpendicular to the field, your charged particle is not moving perpendicular to the field, but it's moving at angle theta to the first place. You want to find out the magnetic force acting on it, you will need to use FB is equals to BQB sine theta. Okay, because when you do that, you're actually considering this one, this velocity here. If you try to resolve this velocity, this one is actually V cos theta. This one is actually V sine theta. So it is this component of velocity that actually produces your magnetic force. So your magnetic force becomes this expression itself, because you're trying to take the component of velocity perpendicular to the field. Okay, so for your case here, the magnetic force acting on your charged particle is PQB sine theta. Alright, now this component of velocity perpendicular to your field is what causes your charged particle to move in a circle. Okay, so if you consider this component of velocity, this component of velocity will produce a magnetic force to cause particle to move in a circle, right? Whereas the component of velocity parallel to the field, there is no magnetic force because it's parallel to the field. So what will happen is that if you consider this component of velocity, your charged particle will continue moving forward with speed v cos theta. Alright, so now this part of your motion, the velocity perpendicular to the field, will cause you to move in a circle, but the velocity parallel to the field will actually cause you to continue moving forward with speed v cos theta because of Newton's first law. Okay, without any resultant force, your charged particle will continue moving in a straight line with constant velocity or constant speed. Okay, so at one end you're trying to move in a circle, and then on the other end you're trying to keep moving forward. So the combination of these two motions is what causes you to have a helical pattern. Okay, because you're moving in a circle at in one side, and then at the same time you're trying to keep moving forward while you're moving in a circle. So that causes you to have a helical pattern here. Okay, the combination of both motions simultaneously, you trying to move in a circle and you trying to move forward, is what causes you your helical pattern. Okay, right. If you're wondering what is the circular motion here, you can try to analyze the motion here. How does the circle look like? You can try to analyze the motion here. Say for example, this one is a electron. Okay, I tell you that this is an electron. The electron is trying to move this way for this part. Your direction or conventional current would be here. Okay, and then your magnetic field direction is here. Okay, if you use Fleming's left hand rule, which is actually FB, B, and I, you will notice that the moment you try to orientate your fingers according to these two different components, the B and the I, you will notice that your magnetic force is actually coming out of plane of paper. Okay, so your charged particle is trying to move in a circle where it's coming out of the plane of the paper and going back into the plane of the paper. But at the same time, you're trying to move forward, that causes you this helical pattern here. Okay, so that's why you get this shape. Now, there's a question that's based on this. If you just look at page 36, 37, that one is from your group chat. The separate sheet is already inside your group chat. If you have this paper printed out separately under June 2019 P42, you can refer to that straight too. Okay, so June 2019 P42, I'll just go through this. This is 36 to 37. This one is June 19 P42. Okay, so let's go through this. This one is question 8. Okay, right now, so they tell you electron is traveling in a vacuum at speed of 3.4 times 10 power 7 meter per second, the electron enters the region of uniform magnetic field of flux density 3.2 millitesla as shown. The initial direction of the electron is at the angle of 30 degrees to the direction of the magnetic field. When the electron enters the magnetic field, the component of its velocity Vn, normal to the direction of the magnetic field, causes the electron to begin to follow a circular path. Okay, this is what just now I was talking to you about. You could have your electron here right now. You actually have a velocity V at angle 30 degrees. You have two components of velocity to consider. One is your Vn, which is the velocity normal to the field. Another is your Vp, which is your velocity parallel to the field. As I mentioned to you, your velocity normal to the field is what causes you to have a magnetic force, which in turn causes you to move in the arc of a circle. So here the question just asks you, find out what is the component of velocity normal to the field. It will be V sine 30. You get the answer as 1.7 times 10 power 7 meter per second. Then after that, find out the radius of the circular path. Okay. So this one, as I mentioned, it causes Fp, which in turn causes circular motion. This one, no Fp. Okay. So this component of velocity in this direction perpendicular to the field is what causes you your Fb and subsequently your circular motion. So your magnetic force provides centripetal force, Fb equals to Fc. So BQVN equals to MVN square over R. Okay. Your V's, please make sure you are careful about the V's that you use. You're not using this V. You're using the velocity perpendicular to the field. Okay. Because if I want to see another way, put it this way, if I try to look at this this situation here from the side, what I'll see is something like this. Magnetic field going into the plane of the paper, whereas my charged particle, the electron here, the velocity perpendicular to the field is this one. Okay, that one in turn causes you to move in the arc of a circle like this. Okay, so here FB is FC, it is BQVN MVN square over R. Okay, that is how I got this. Okay, this one is the view if I look at it from the side. This is what I see. Okay, that's why I need to use that Vn, not any other velocity, not the parallel velocity, not the resultant velocity. So you sub in what you have there, you get the answer at 0.032 meter. Okay, so that part is okay. Right. So okay, now after that, the next part of the question asks you, state the magnitude of the force, if any, on the direction. State the magnitude of force, if any, on the electron in the magnetic field due to the component of velocity along the direction of the field. It's asking you about the velocity parallel to the field. Would there be any magnetic force there? The answer is no. Okay, it will be 0. Okay. Then after that, they ask you use the information from here, from A and B, to describe the resultant path of the electron inside the magnetic field. How would it look like? So as I mentioned to you, your charged particle is trying to move in a circle due to the vertical component, due to the component of velocity perpendicular to the field. Okay, it's trying to move in a circle like this. If this one I extend the magnetic field a little. Okay, your charged particle is trying to move in a circle like this. But at the same time, this component of velocity is trying to push you forward. So while you're moving in a circle, you're also moving forward. That one causes you your helical pattern. We call it unique so-called pattern. Alright?